here. All right, so we're still working with addition. Next, we have the chip and charged particle model. I'm going to throw them together. So addition of integers. We're going to look at chip and charged particles. And there's lots of reasons you might pick one over the other. I mentioned a couple. Sometimes it could be you have a classroom that just has a set of colored chips or some real or fake coins, like heads and tails are good, I mentioned in the activity. It could be kids are drawing a lot on paper, in which case, sometimes if they just have a pencil for the chips, I might do something like an open unshaded chip versus a shaded chip if I only have one set of colors. So alternatives here are, we might use this for our negative, and this one could be our positive. It could be you have a set of chips in the classroom and maybe they are red and black, but sometimes they're red and white or black and white. So whatever you have at hand to play with, but it is kind of nice to play to get the kids the idea of cancellation, the zeros that pop up. So again, we could have that version of charged particles. It could be we actually have red chips in the classroom for negative, and black. I have a couple of sets that are a different color on each side. So you flip it over and you get a different color. Some of them are white and black, some of them are red and black, some of them are red and white. And then alternatively, I have the minus and the plus for negative and positive. And regardless of which version I use, we got to throw in a 0, and that's when we throw two of these together. So there's a 0 there, and up here, if I throw two together, that's a 0. And with my colors, two different colors together make a 0. And the 0 idea and that idea of opposites that cancel, that inverse idea, are pretty powerful, but they also make things really complicated and people struggle. I mean, think about it. How often is the mistake you made in math, algebra type stuff, a sign? You messed up a sign, either addition or subtraction or a multiplication of a sign. Gets me all the time. So addition kind of means the same thing it did before. Addition means combine and count. Okay, so whenever we do, for the next couple weeks, a problem where we're trying to model sign numbers and we're using any model, oops, I missed my L there. Doesn't matter whether it's the number line model, the charged particle model, the chip model, we got to do a couple of things. We have to say, okay, what is our model? Is our model the numbers the arrows that point in a particular direction? We have to be upfront about what that means, which direction they go. Or if we're using the chips and the charged particle, we got to say which symbol is a negative, which symbol is a positive, or which thing, if we have physical things in the classroom, is a negative, which is a positive, and a reminder about what a 0 is. So you have to have a key, and then you have to have a definition for what the operation means. So in this case, addition means combine and count. With the number line, addition meant the arrows are combined front to back starting at 0. So we need essentially two big things in order to do any model, any operation. We need a definition of what it means to put stuff together, and we need a key for what we are putting together. Okay, what are these things? So I'm going to go with the first version of the chip model, where I'm just going to use a single color. Open circle is negative, a solid circle is positive. Two of them together is a 0. And just look at a couple of examples. So let's look at, let's say, example A, B, and C here. So A would be to model 2 plus 3. B is going to be to model -3 plus -3. And C is going to be to model -3 plus 4. So I'd like you to give this a little head start on me. Write down, we already have our definition here. We have our key over here. This is the key I'm going to use. What I want is a picture with a brief explanation of the answer based on the definition and the key. So write down, draw a quick picture, quick explanation with each one of these. Let's see if we can get something pretty similar. I'm going to pause for just a moment while you guys scribble. So first couple are pretty straightforward. I have a set of 2. I combine that with a set of 3. I recount it up and say I got 5. No problem. Brief explanation with my picture. Next one. I've got a set of -3 combined with another set of -3. I combine them together. I get a set of -6. Pretty straightforward. All right, let's do my next one. So in this one right here, I could just leave the final answer looking like it is, or I could rewrite it and just say, well, you know, the zeros could just go away. I could take them or leave them. I could just say that's my answer right there at the end. So when I put these together, I do have to acknowledge that I could make a whole bunch of zeros. And so let me just highlight those to be clear. When I put those together, I have 1, 2, 3 zeros, and then I have this leftover, oops, and that is not a -1, I lied. Double check my key. A shaded is a positive. Always check your key. Is a +1, so I guess I'll be extra clear. The sum there is +1. Okay, for my slight goof at the end, does anybody have a question about that last one? Nothing in the chat. I hear no voices. Hopefully my sound is still working. Can someone acknowledge they can hear me?
Yeah, it's still good.
Cool, thank you. All right, so there's no questions on that, right? So we combine them together. It turns out we make a bunch of zeros, and I end up with a +1 left. That's the way it goes, right? So the charged particle model looks pretty close to the same thing. So just for fun, I'll draw one of those on the next page. You can do it with me. Let's do an example D. Then we get to talk about subtraction. Let's say example D is -5 plus 3. So if you could draw an illustration based on this key. So this is a positive, that is a negative, and this is a 0 when we put two of them together, and addition means combine and counts. Make a quick sketch. One, 2, 3, 4, 5. 1, 2, 3. Okay. So I'm gonna circle that as my new set. But I could rewrite that as just two negatives, since I have 1, 2, 3 zeros there. So the net charge here is a -2 for the final answer. Not too bad. Questions? Nothing in the chat yet. All right, next, fun with subtraction. This is probably as far as we'll get today. I want to talk about the activity. All right, so with subtraction is a lot like addition. We have to know what subtraction means, and we have to have a key for the things that we're working with. So let's do this in reverse order. Since we just finished the charged particles, let's do charged particles. So we're going to say integer, the integer key here, integers, just like before, we got our +1, we have our -1, and we have our 0. Hopefully we're getting more used to that. Then we have to know what subtraction means. And we have a couple of options there. Subtraction, the two main things we used before for physical modeling were either it means take away or it means comparison. And I think I'm going to do takeaway first. So what I'm going to try and model is a pretty straightforward one. So let's call this example A for subtraction. We're going to take 5, take away 3. So to do this right here, I would start with 5, right? So I'd say, okay, well, here's 5. 1, 2, 3, 4, 5. And then, so there's my initial set. Now, I want to take away 3. So I'm just going to redraw that. 1, 2, 3, 4, 5. And then to take them away, I could maybe like circle them and say, take these guys away. Right. I could have drawn that in the first picture, but I'm going to do a sequence here of pictures. So that was my first step. And now I'm going to try to take away, and I'm just going to make a note that that leaves 1, 2. So the answer is 2. You could have done this with just one picture, making a note of what you're doing there. That would have been okay too. Another example. Let's get more interesting. What if I wanted to start with 3 and then take away 5? So we would have to draw a set of 3. And then now I'm going to try to take away 5. But I can't. There's only 3 positives there. I can't take away 5 positives. What am I going to do? I remember. I can rebuild 3 to look different. Rebuild 3. So that's 3. So is that. So is that. This still is 3, but now I can take away 5. Period. That leaves what? Well, that's going away, 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 right? Take away. And so I have -2 left is the answer. So sometimes in order to do the operation we have to build some zeros to get enough charges or particles to take away. Doesn't matter whether I use the charged particles or a chip. We're going to do a chip next. Same idea. Questions on that example? All right, example C, I'm going to change the key on this one. I'm going to do just 2 colors, so I don't have to change pen, or just 1 color, so I don't have to change pens as much. So I'm going to have this one up here be the negative, like I did earlier, and this one's going to be the positive. If you want to play with colors, go for it. Just make sure you have a key for your colors, and then you should also show what 0 looks like. And I'm still going to stick with the takeaway model, so I'm still going to say subtract means takeaway. We'll look at comparison next. And let's try -3 minus -5. So if I wrote a sentence about what that means, I would say from -3, take away -5 is what that's telling me to do right there. So like before, I have to show where I'm starting. What does -3 look like? So that's -3. But at the moment, I can't take -5 away because it's not there. Okay? And what am I trying to model here? I am trying to model takeaway. So for any of you that are trying to change some signs, stop. Because we're not modeling addition here, we are modeling subtraction. So next thing I have to do is I got to rebuild that -3 so I can actually take away -5. So rebuild -3. So here's my original -3. So I'm just going to start throwing in here. Oh shit, I said I was going to do the circle ones. Bad Gary. All right, ignore that picture. And let's redraw it with the circles. I mentioned earlier I like the charged particles. So we're still going to follow those directions, and then over here we're going to throw in some zeros. That's still -3, but I don't have -5 to take away, so I do it again. So this, oops, accidentally erased it. This is my set. This set right here still has a charge or a net value of -3 because I have a couple of zeros in there. Okay, so now I'm going to take away the -5. And so maybe I will redraw that and just cross some out. So that's gone, that's gone, that's gone. 1, 2, 3, 4, and 5. There are 2 left over. So the answer is +2. So sometimes if there's not enough of whatever we're trying to take, we got to build it in there in order to take it away. Question on this example? All right, next example. Let's call this example D, and we're going to change models again. We're going to look at the number line model here. And let's try the number line model for, how about 3 plus -5. And so on a number line, I just want to make a note of what some things mean there. Positive is a right-facing arrow. Negative is a left-facing arrow. And then 0 is no movement. That's important in case we need it. And then what does subtract on a number line mean? So I'm just gonna, takes a little bit more room. Subtract on a number line means to first change the direction of the second arrow. And then combine back to front. Starting at 0. So remember, for addition, the main difference can't be exactly the same because adding is not the same as subtraction. We just combined back to front starting at 0, but now we're subtracting instead, so it's got to be a slightly different set of rules, and that first change, the direction of the second arrow, is how we interpret subtraction on a number line. There's another way to do it that's kind of fun with a car, where you know, positive is to go forward with the front of the car, negative is to go backward, and subtract means turn the car around and do whatever the arrow says. So we can take a look at that in a sec too. So we need a number line. And some numbers. And 0's got to be in there. So we have 1, 2, 3, 4, 5. And the other way, 1, 2, 3, 4, 5. And if you're having trouble being neat, try to find some graph paper or just pay extra attention or get a ruler. Ooh. All right, so first change the direction of the second arrow. So at some point, we're going to need an arrow that's 5 long. And at first, a -5 would look like this right here, right? Starting at 0, 1, 2, 3, 4, 5. Oh, I wrote add up there. Why did I do that? Let's fix that. So that should be 3 minus -5 is what I'm trying to do here. And so we're going to have to change the direction of this. So I'm going to start with my 3 arrow. So from here, just draw underneath, I'm going to go 1, 2, 3, and stop. Now, normally -5 would have me go back that way, but I got to change direction, so I'm going to go the other way. So I'm going to have to go 1. Oop, my number line's not big enough. Let's see, 6, 7, 8. Let's go out to 9. So from where I left off here, I need an arrow that's 5 long, but in the other direction because I'm subtracting. So 1, 2, 3, 4, 5, double check. From here, I'm going 1, 2, 3, 4, 5. So I'm just looking at the ruler above as I make those marks. So this would be, again, 3 minus -5 takes me over to 8. Is the way the number line model works for subtraction. And the big thing is we have to change direction of the second arrow. If it said go left, subtract means no, please go right. It said go right and we were subtracting, we'd say no, please go left. Okay, I think those are the main things I wanted to get to right there so that we can take a look at the activity. So for this one right here, you can use whatever you want for toys. Maybe you have some pennies at home, or you can draw pictures on a piece of paper. But you have to have some kind of key for me that tells me up front if you're going to use the same thing all the way through. And I'd recommend picking some model and going all the way through with it. So maybe you have some colored chips for some game. Maybe you have a whole bunch of coins at home. Recommendation for coins is heads is negative and tails is positive. But you need to write your key down. We did problem number 1, at least parts of it, where we represented an integer in 2 different ways with the coins. So just a reminder about that. It's way back here when we first started talking about models. Yeah. So for example, -3 in the chip model could look like this. It could also look like this one over here. Or it could look like this one down here. So all of these are representations of -3. Now notice one of these uses the fewest number. Oh, my pen stopped writing. Why is that? There we go. This one has the fewest number of chips to make -3. And that is an important idea. Again, I'm not quite ready to talk about that yet, but we will soon. Maybe you already know what it is. Let's blow this up a little more. And then whatever model you chose for your representations up here, whether it be red and black or open and colored circle or pluses and minuses or heads and tails, you want to use them to model each of these right here. Now, when we model these, again, we want to have our key on the same page. We also need to state what it means to add. And so far we've used takeaway. So here I'm saying show how to use the takeaway model and the chips or coins, or maybe you're going to use the pluses or minuses to demonstrate each of these right here. So -3 minus -2, -3 minus 2, 3 minus -2, -3 minus 5. And again, for each of these, you got to show a takeaway. Okay, I know that you've learned the algorithm where we change the signs on the paper, but that would change the problem to addition. For number 3, I don't want to see any addition modeling. It's got to be subtraction. What that means is sometimes in your subtractions, you're not going to be able to do the takeaway. You're going to have to rebuild by adding some zeros in so you have enough of whatever you need to take away. And it could be you're rebuilding to get extra positives. It could be like in the next example here, I had to rebuild so I had enough negatives to take away. Okay, so that one is a little tricky. So please be careful on that. So your pictures for subtraction do not look the same as addition because we're not combining, we're taking away. And you have to show that you're definitely taking away that second number. So no changing. Questions on the activity?
Not at the moment, no.
Okay, so this isn't due right away. It isn't due until I think next Wednesday. Where does it show me that? I have to go to the home screen, I think. December 2nd. Yeah, so that's next Wednesday. So if you turned it in early before we went over this, you might want to say, I'm going to turn it in again after this. So I did notice a couple of people turned it in early. There has to be explanations. If it says subtract, you got to show a subtraction and what you're pulling out. So if you did already submit, rethink it and make sure you're right. I allowed for another submit on this one here if you need it. And I mentioned there are 12 main topics in this section. We've gone over about half of them now, I think. Yeah, we've talked about a little bit of properties, the commutative property, the property of opposites. We've looked at a bunch of definitions of opposite. So yeah, I think we've gone over about 6 of the 12. And so we'll do our best to finish them next time. So next class, we need to go over multiplication, division. We'll review addition and subtraction because we need them to do multiplication and division. And then there's just some algorithms that we have to go over, and we'll build those algorithms together. So algorithm is where I don't draw a picture, I just have a procedure that gives me an answer, right? So what is exactly the procedure, the algorithm for subtraction? So let's just, actually I wanna mention that right now and then I'll shut up. Where's a new page? The subtraction algorithm is pretty straightforward. Addition is actually harder, in my opinion, for integers. So I'm gonna mention the integer subtraction algorithm, and then we'll nail the addition algorithm next time. So integer subtraction algorithm is that we rewrite subtraction as adding the opposite number. That's it. Now it's an addition problem, and then we just look at the addition algorithm. And the addition algorithm has multiple steps to it. It's a little more complicated. We'll nail those steps next class after you've had a little bit of time to play with this activity. So my hope is that you've tried to complete this activity by Monday's class so we can go over it together, because we need to do the activity in order to nail down the addition algorithm. So for example, subtraction algorithm says, well, if I needed to do 3 minus 5, it says to rewrite that as adding the opposite of the number. So according to this algorithm, 3 minus 5 is the same as 3 plus negative 5. Now, some of you might look at this and say, well, I'd rather just think about it as 3 minus 5. Some people might like to think of it as 3 plus negative 5, but that's the algorithm. Similarly, if I had 4 minus negative 7, that becomes 4 plus the opposite of negative 7, which is 7. Oh, that one's easier there. Negative 6 minus negative 8 becomes negative 6 plus 8. Negative 7 minus negative 6 would become negative 7 plus 6. So all the subtraction algorithm says, it just tells you how to change subtraction into addition by taking the opposite of the number you were subtracting. So this is super important, and this is one reason I mentioned the subtraction algorithm right now. If I asked you to model 4 minus negative 7, and you instead rewrote it as 4 plus 7 and showed me what the model for 4 plus 7 looks like, that's not the right model, because I wanted to see a subtraction model, not an addition model. And modeling 4 plus 7 looks totally different than 4 minus negative 7. Okay, so please keep that in mind. Don't go applying an algorithm where you're changing subtraction to addition. You want to actually build where necessary when you don't have enough of whatever to subtract. Okay, so give that a shot. Message me if you get stuck on anything. We'll go over this again next class, and then we'll move on to nailing down what the heck is the addition algorithm for integers. Why am I leaving it off? Why do I say subtraction algorithm's easier? We'll see that when we actually write it down, what it means to add. And then we'll move on to multiplication, division, and a few other properties. And then we're done with new stuff in the book, and we get to get ready for the final exam. So I am going to stop here and stop.